Hi everyone, my name is Caroline, and today I am presenting a position paper towards requirement specifications for machine learning perception based on human performance. The application of machine learning-based perception algorithms in autonomous vehicles is very popular these days. Some of the accidents involving self-driving cars, it is considered whether the current ML models are safe to be used in autonomous vehicles. But can we actually assure safety of such systems? This is a very challenging task. Part of it is because unlike normal systems designed to follow a list of carefully defined requirements, ML learns its behavior through data. For safety-critical systems, where mistakes pose risks to human lives, safety guarantees are crucial, and knowing the expected behavior is the necessary first step. Past work suggested these properties when evaluating an ML model: performance, robustness, reusability, and interpretability. We now only focus on the robustness requirements. It is a well-known fact that ML models are vulnerable to adversarial attacks. Like shown in this image here, small changes in the images can cause ML models to misclassify the signs. This is clearly undesirable behavior. Past work on testing and verifying robustness of ML components only focus on checking the robustness within an intuitively small neighborhood. For example, changing a few pixels, like in this example here. But some questions still require further investigation. For example, how should this neighborhood be defined? How should the resulting requirement look like? And we propose to use human performance as a baseline to express and formally specify a subset of minimal expected input and output behavior of MLCs. Using human performance as a baseline, we will assume that perception MLCs are required to be robust to any input modification that will not change human perception. This means that if humans are able to correctly classify the objects after the modification in the input images, so should the MLCs. For our purposes, we're only considering modifications that can be formally expressed as transformations. For example, affine transformations and transformations modifying different aspects of the perceptual context: light sources, medium, objects, and observer. In this case, it's the camera. So we then further refine the requirements to invariant and equivariant requirements, depending on how the modifications in the input could affect the output. So invariants are further divided into changes that are not visible to human and changes that are visible but preserve the structure of the objects, and therefore do not affect humans' ability to recognize the objects. So the distinction is important here because if the modifications are non-visible, it has to be invariant, and visible changes must be argued separately. For MLCs like object detectors, in addition to the label, they produce bounding boxes to indicate the extent and location of the objects. For transformations like translation, the location of the bounding boxes should move a corresponding amount, and for scaling, the extent should be scaled correspondingly as well. But the label should always be preserved. Therefore, these are equivariant. Finally, to formally specify a robustness requirement based on a transformation, we need to determine the range of modifications for which an MLC should be invariant or equivariant. For example, there is a bound on the amount of noises that can be added before a human will no longer be able to see the objects in it. So to summarize, our robustness requirement for a perception MLC consists of these components: a formally defined transformation over the inputs of the MLC, a range of values for the transformation parameters, and an indication of whether this is invariant or equivariant. And to derive the robustness requirements, we follow this simple procedure. First, we identify types of modifications that humans are invariant and equivariant to when recognizing objects and images. To do this, we use studies of human visual system. The HVS system is shown in this image. You can sort of view HVS research as studies of human perception. So based on HVS research, we know that spatial shifting and rotation do not change human interpretation of the image and therefore should be equivariant. Noise is shown to well-preserve local structure of an image and therefore should be invariant. In the next step, based on the types of modifications in the previous step, we identify transformations to formally define the modifications. For example, for noise, a transformation could be adding Gaussian noise. Below is an example of adding Gaussian noise to an image. In the last step, we need to determine the range of parameter values for the transformations. We propose to do a search through the space of parameter values along with an oracle that determines whether the transformation with a given parameter value is invariant or equivariant for humans. For example, the oracle should be able to tell us whether the noise in this image is too much that a human won't be able to recognize the objects in it. One possible choice for the oracle is image quality assessment metrics. IQA metrics uses studies of HVS to evaluate whether changes in the image can affect human perception. There are many different IQA metrics with different capabilities. Some check the perceivability of distortions, some focus on checking whether the structural changes are significant, and some check for perceptual loss of quality. One example IQA metric is visual noise to signal ratio. VSNR can determine whether the changes are visible to human. Being robust to non-visible changes seems trivial, but do the state-of-the-art object detectors satisfy this? The image shown on the left is the original image, and the one on the right has some non-visible noise added. If we check the YOLO detection for these two images, we can see that the sign in the red box is misclassified as a traffic light. In addition, a car below the sign, which was not detected before, it's now detected. This shows that YOLO is not robust to non-visible noise added. Mistakes like this can have serious consequences in safety-critical systems, and therefore the use of this version of YOLO would be unsafe. To conclude, we have emphasized the importance of requirement specifications for MLCs. We proposed a method to specify the robustness requirements based on human performance, which is approximated using HVS models. And we have also demonstrated that YOLO is not robust to the non-visible Gaussian noise. But more importantly, there are many more questions that remain open for future investigation. For example, which IQA suits better for different types of transformations? How do we deal with changes that cannot be expressed as transformations? Can we use other studies except for IQAs as the oracle? Thank you.